let's get started with lecture number 33. Can you hear in the back? Okay. Announcements. 1. We have weekly one-on-one tutoring posted on Piazza. We just gave a survey, which many of you filled out. The people who go to this tutoring love it. Just thought I'd let you know in case you want to sign up for tutoring. It's now a pinned post. You can still sign up today. Speaking of course surveys, there's one out right now, and I'm asking that everybody complete it today. If 85% of students complete it, everyone gets a point. So far, 63% of students have completed it. So you're a long way off. If you know someone in this class, you better harass them until they complete the survey. There's the link. It's also on Piazza. It's also on the top of the course website. Everywhere you look, you will see this link. Spend 5 minutes and fill it out. I assume the chatter in the audience is people harassing other people to make sure that they finished the survey. Thank you for that. Are there any questions? Okay, project 4 is due this week. It's due on Thursday. If you submit it all by Wednesday, you get an extra point. Why not? There's also a recursive art contest. Entries for that are due a week from today. In order to submit them, just take a screenshot and send your code to Albert, cs61a-tae@imail.eeks.berkeley.edu. He's going to take all of your screenshots, put them together into a gallery, and share that with everybody. Yeah, you got to finish the extra credit on when... No, if you don't do the extra credit, you can still get the point, but you don't get the extra credit points. But you can't then go back and do the extra credit and still get the early point. Does that make sense? No questions, huh? Oh, yeah, question in the back. No, you don't have to do any recursive art in order to get extra credit. There's one recursive art question in the project that's totally optional, you can do it or not. And then there's the contest, and that's totally optional, you can do it or not. Okay. How is that project, by the way? It's amazing. You're building an interpreter. That's incredible. Yes, building an interpreter is a non-trivial exercise. It's one that many students don't try to do until much later in their CS careers. So if you make it through, you should feel very pleased with yourself. Okay, so we've been talking about the declarative language called the structured query language, or SQL or SQL. And you might be wondering, what's the deal with this language? It's all so simple. There's no crazy recursion or anything like that. False. Today we learn about recursion in SQL. Oh, by the way, homework 9, I haven't posted yet. It's actually just part of homework 10, so we'll have a 4-point homework instead of a 2-point homework, and it'll be due next Wednesday, so you can focus on your project this week. Okay, so we need to build up a little bit of machinery before we understand how you can build tables recursively. And the first thing we need to know is the difference between a globally defined table, which we created using the create table statement, and local tables. So local tables, like local names, only are used in the context of evaluating a single statement. So create table statement creates a table globally, and other statements can go refer back to its name. And we did this already. We created a table of parents, which listed the parent and child among all of my dogs, and which I name after U.S. presidents. And so this select statement, union, will create all the rows of the parents table, which I can then refer to in later statements. And the actual table looks like this, but we've been drawing it like this just to remember what's going on. Hopefully all that is review. In order to create a local table, we use a with clause. A with clause of a select statement names a table that is local to that statement, meaning it's created for use in the select statement, and then it becomes inaccessible, so you don't need it anymore. So let's say I have my very favorite dogs, Eisenhower and Barak. They're the best. And I want to make sure that I have more dogs like them, so I want to figure out who are the parents of my very favorite dogs. Now you should already be able to write down a select statement that picks out the parents of both Eisenhower and Barak, just by comparing and using OR and hard-coding those names into the where clause. But maybe there's a better way. The better way is that we're going to place the names Eisenhower and Barak into a local table, the ones filled with my very favorite dogs, and then I'll refer to that table in my final select statement where I select the parents of my very favorite dogs. And in order to create a local table, I include a with clause. So this whole thing down here is actually one big select statement where I precede it with the word with, which is a keyword in the SQL language, followed by the definitions of all the local tables that I will refer to, and then it ends with the part that you're familiar with, where you say select, and then the columns you want, and then from, and here you can name global tables, and you can also name tables that were defined within the with clause. So I say, here's a new table. It's called best. It's full of the best dogs. And best dogs is defined by a select statement that looks like select Eisenhower union select Barak. And then I stop defining new tables, and I can complete the entire statement by saying, please give me the parent from the table that I get by joining all the parents with all of the best dogs. So the best dogs is a table with one column called dog, which has Eisenhower and Barak as the two row values. And so if I join parents and best together, I can refer to child and parent as the two columns of the parents table. I can refer to dog as the column of the best table. And so if I say child equals dog, that gives me the rows that say things like Abraham is Barak's parent and Barak is the best dog. Selecting parent from that will give me the output Abraham. Okay, there's a lot of quirks to this syntax. It's kind of like what syntax should have been used for SQL all along if they had thought of that, but they didn't. So they added it later. So the with clause and the select clause and the kind of whole select statement look a little bit different. Let's go through all the details of how they're different. When you say with, you give the name of the table immediately. So with is kind of like a create table with a select in it. You say with the name of the table, and then you put parentheses, and then you put the names of the columns in that table. So I'm creating a table called best with a column called dog. If I put multiple different names within parentheses, then that would create multiple different columns in the local table that I'm defining. Okay, so we have name of the table, name of the column as. We have parentheses. Normally, select statements don't have parentheses, but with clauses are special, so they do have parentheses. And you put those parentheses around stuff that's going to define the contents or rows of this new table. So here I say select Eisenhower, union select Barak. Notice that I didn't have as, like I would here, to define the name of the column, because I already defined the name of the column up here. The name of the column is dog. So it's separating column naming from putting contents in the rows, by putting column naming up here, and all the contents are defined within parentheses. And you have to close those parentheses. You can actually define multiple different local tables just by having another one followed by a comma. We'll look at that a little bit later. And then eventually you have to say select. And this select statement here can reference the best table anywhere that it lists a table, which is within the join column. That's where you list the tables that you're projecting. So every select statement creates a new table from some old tables. Now you can put best in your list of old tables. We could reference best directly. Okay. So best only exists with this select. So this select can reference best. Other ones can't. You don't need to reference anything else if you don't want to. And let's take a look at that example. So this is exactly not at all what I had on the screen. This is exactly what I had on the screen. So this is all the parents, and then this is with best dog as blah, blah, blah. And when I run this, it says loading resources, and then it says Abraham. Why is that? Well, that's because that's the value of this thing. If I run this whole thing, it lists a one-row table where the parent is Abraham. Now you were wondering, could I just get rid of the parents and do something much simpler, like say, select the dog from the best dogs? That I could do as well, and that would list all of my favorite dogs. So this defined a table and then selected its contents. I think the question is, how do you define a local table with multiple columns and keep everything straight? So if I wanted to define the dog and the owner, I would just list them in order. So John owns Eisenhower and Jack is here. Then I could just select the dog. And if I wanted to list both the dog and the owner, it would go like that. Other questions? So let's go back a second to our original example. Start over, just so we have a clean slate, we know what's going on. Since it's the case that parents was defined globally, I can always refer to it. But I can't do anything with best. It's gone. If I want to use it again, I would have to copy and paste this whole with clause into a new select statement and use it there. Yeah, you can create multiple local tables. I can just do it here. I could say, here's the worst dogs. Oh, I'm not even going to name the worst dogs. That's not right. But you get the idea. Okay. Here's one for you. Your job is to figure out what are reasonable names for the column here and here that result from writing down this local table, which I've unhelpfully called what, and then I've joined it with parents, done some condition, and thereby expressed some relationship between pairs of dogs. So what is that relationship? Try to figure it out. Read through the code, talk to the person next to you. You have a couple minutes. Go. Let's see if we can figure out some appropriate names for the columns in this result, and then we'll look at a second question that are how many rows and columns actually do result. First of all, can we come up with a better name than what? Okay, we have a vote for siblings. That's what I picked too. So what this says is, picks out two different things with a common parent. So we have Delano and Grover, our siblings. Okay, and then this says select the child. Now what table does child come from? It comes from the parents table, because parents has two columns, parent and child, whereas siblings has two columns, first and second. So child must come from the parents column, so we want child-parent pair, and we're picking the child. And then second comes from the siblings column. And second is the sibling that's not first. This constraint says that the parent from the parents table should be the same as the first from the siblings table. Okay. So if Delano and Grover are siblings, and Delano's the parent of Herbert, then we can see the parent is the same as the first sibling. And what we're listing out is the child Herbert and the second sibling Grover. So what's the relationship between Herbert and Grover? Or here's another example. It's the sibling of my parent, would be a nephew and an uncle. Oh, yeah. Are Abraham and Grover siblings? Yes, they are, in a different row than this one. So there's like lots of different rows. I picked the row where Abraham and Delano were listed as the siblings, but there's another row where Abraham and Grover are. Okay, so the question is, how does this work? There is an order to which things occur conceptually. Now remember, it's up to the interpreter to figure out what order to run things in because it's a declarative language. But you still need some way to think about what it's going to do. So you are safe to assume that you build up this table locally first, and that it's really populated with all the contents of every sibling pair in this example. And then the select statement is evaluated, where it pairs up every parent-child pair with every sibling-sibling pair, throws out the ones that don't meet this condition, so it keeps things where parent equals first, and then it pulls out two columns from that, the child column, which we'll call nephew, and the second column, which we'll call uncle. So this join builds long 4-column rows like that, and then the column description above it, which comes between select and from, tells you which ones you want to keep. Excellent question. Mediocre explanation on my part, so if anyone has more questions, feel free to ask. Okay? Here we go. Recursion time. So it turns out that a local table can refer to itself, and thus we get recursion. What does it mean to refer to itself? Well, that means that it's defined in terms of a select statement which has a from clause, and that from clause names the very table that you're creating. So here's what we're going to create first, an ancestor table. An ancestor is either your parent or an ancestor of your parent. That's a recursive relationship. So anyone up on your family tree. So let's say we have the parents table already, and we want to know who are the ancestors of Herbert. Well, that would be Delano and Fillmore and Eisenhower. So all the way up to the root. In order to define that, we're going to have to build a local table called ancestors. Ancestors is going to have two columns, the ancestor and the descendant. So it'll have stuff like Fillmore, Herbert in it. Here's the whole definition. You write down the base case, select parent-child from parents. And what this base case does is it says one form of ancestor-descendant pair is just a parent and a child from a table that I already know. So in the ancestors table, there's a row corresponding to every row in the original parents table. But there are more than that. It's also the case that there's a row for every ancestor-child pair that you get by taking an ancestor and a parent, joining those two together, making sure that the parent is the same as the descendant, at which point the child is the descendant of the descendant, or the child's parent's ancestor is an ancestor. So that's the second case here. Your ancestor is an ancestor of your parent. So the descendant is the thing that has the ancestor. So if the descendant is the parent, then the ancestor is the ancestor of your parent. Okay, this is actual syntax and actual SQL, actually runs, except that this is a local table definition, and we need to put it inside of a with clause. And a with clause can't stand on its own. It's always part of some select statement. So all this other stuff here needs to be written down in order to have a legal statement. So you can locally define this recursive ancestors table, and then you can ask something about it, such as what are all the ancestors where the descendant is Herbert? And that will look at all the different rows, select all the ones where the descendant is Herbert, take the column full of ancestors, and print out the contents, and the contents will include Delano, Fillmore, and Eisenhower. Question? If you write it such that it runs forever, it will run forever. In this case, there's only a finite number of ancestors, and so, yeah. If the contents of the table is finite, it will compute that contents in a finite amount of time. Yeah, so try not to define infinite tables. Okay. So here's what you get out. Delano, Fillmore, Eisenhower. There's like so much going on here. We have a base case, you union that. When you have a union, we have like not just one row here, but many rows generated by this first select statement. And then we have many more rows generated by the second select statement. And union just puts them all together into one table. The column names of that table are ancestor and descendant. This defines some rows, and this defines other rows, and these rows, most importantly, are defined by joining ancestors with parents, and these rows appear in the ancestors table. So that's where the recursion comes in. Whoa, that's intense. Questions? Yeah. So how do you know it's a base case? Unfortunately, you don't write down conditions in SQL in the same way that you would in Python. So it's hard to tell what the base case is and what's not. The reason I called this a base case is that it's not defined in terms of the ancestors table. So it's not defined recursively in any way. So it's almost always, so it's always going to be the case that you'll, when you have a recursive definition, you also need some contents that's not defined recursively to get you started, and that's analogous to a base case. So that first base case makes sure that the ancestors table contains all parent-child pairs. So it contains the fact that Delano is an ancestor of Herbert. That's what the first line does. The fact that Fillmore's an ancestor of Herbert comes from the second one. Ready? Okay. So now we're going to try to give global names to anything we recursively define. Unfortunately, it's remarkably hard in this language. You have to define the thing as a local table and then make a create table statement where you select all of its contents. So let's say I want to define all of the odd numbers up to 15. I have to say create table odds as, and then I actually go about defining the odds table as a local table. So with odds n, the odds table with column name n as the number 1. So that means we're going to have a row with 1 as the value. And then we're going to have rows with n plus 2 as the value, where n is something that's already in the odds table. So 1's already in there, which means we get 3. And now 3's in there, so we get 5. Now 5's in there, so we get 7. And we go all the way up until 15. Now this definition here creates a local table. If I'd like to give it a global name, I actually have to select its contents and create a table with that contents. So it's the create table odds up here that decides the global name of this table. And this is like a projection that does no changes. And here's the result. Oh, so does this create repeats? No, the interpreter's job is to make sure that each row that is created in a recursive definition only gets used to generate one other row. So there are no repeats in the output. You could imagine another world where it didn't work that way, but this is how it actually works. Well, it says if there's any if there's any row in the table that satisfies the where clause, so it's less than 15, then it's going to make sure there's also n plus 2 somewhere as a different row in the table. So the fact that 5 is in there means that 7's in there, and the fact that 7's in there means that 9 is in there. The fact that 15 is in there has no effect because we're only going to use rows where n is less than 15 when generating n plus 2. Okay. Question? So n's the name of a column, and there's a row in which the value for n is 1, created by select 1. And that's the row that is used to create the row containing 3. Yeah, you might be very tempted to say, isn't this a for statement where you're changing in and trying it a bunch of different kinds? And while that might be happening behind the scenes, it's not up to you to figure out how this gets interpreted. All you get to do is define the relationship between a row that's already there and a new row that you want. So the row that's already there has n equal 3. The new row that you want has n equal 5. Okay, which names above can change without affecting the result? If you want a table called odds, you have to say create table odds. But it doesn't actually matter what you call the local table, because local names are gone by the time this thing finishes executing. So I could call this what, and it would still work as long as I changed it in all 3 of these places at the same time. is the great abstraction in declarative languages. All you can say is the relationship that exists between something that's already there and something that you want to be there. So what you've said is for every n, there should be an n plus 2. But how it figures out which n's it's found already and which ones it hasn't, and make sure that it doesn't repeat anything, it's just kind of up to the interpreter, and all the different database engines will do it in different ways. Now you might wonder what actually happens. So what actually happens is that it maintains a list of rows that have been inserted but haven't yet been used to create more rows. And for every one that gets inserted into that queue, it eventually gets used to create another row if it passes the where condition. And stuff like this shows up in search procedures if you ever take an artificial intelligence class like 188, or you'll actually see it maybe in 61B. Okay. How crazy do the examples get? Well, the answer is actually not too crazy. So there are limits on how recursive you can be. Recursive table definitions can only appear in a with clause. You are not allowed to use mutual recursion. So you can't have one table defined in terms of a second where that second one is defined in terms of the first. So it's not allowed that two or more tables are defined in terms of each other. Well, it's hard to build a database engine that can handle all of these different cases, so they just didn't bother. So you can't say odds is defined in terms of evens and evens is defined in terms of odds. It will just say not allowed. Nope. You're not allowed to use tree recursion. So the table being defined can only appear once in a from clause. So you might wish you could define all integers by taking an integer and subtracting one from it, or adding one to it, but that doesn't work. You might wish that you could take all pairs of integers and then add them together to get a new integer, but that doesn't work either. So you only can put ints once within the from clause of ints, and you can't refer to another recursively defined table if that table refers back to your table. Okay, so there is recursion in the language. We'll use it, but there are limits to how it can be used. Yes, it would be very sad if Python had these limits, but we don't. Okay, let's do an example. I know what I'll do. Okay, here's an example from last time. We wanted to come up with all of the sentences that were like, the dog chased the bird. And so we did that by creating nouns, the dog, the cat, and the bird, and then getting all possible combinations of the dog chased the bird by getting nouns, and then making sure that dogs don't chase themselves. So we got the bird chased the cat, the bird chased the dog, etc. But language is actually recursive in its structure. So a noun phrase can actually contain a relative pronoun that introduces a relative clause that has the structure of a whole sentence. I can not only say the dog chased the cat, but I can also say the dog that chased the bird chased the cat. I can also say the dog that the bird chased the cat. Now, in this case, the relative clause is like a sentence where it's missing the subject. So that kind of fills in for the subject. The subject is the dog. So the dog chased the bird and the dog chased the cat. This one's more interesting. So this is, that is filling in for the object. It's the bird chasing the dog chasing the cat. Now it turns out in the English language, the relative pronoun can be dropped and you can still have a grammatical sentence. You can say the dog the bird chased the cat. So it's still the bird chasing the dog chasing the cat. And you can nest these arbitrarily deeply. So I could say the dog, the bird, the cat chased me. Who's chasing whom? The cat's chasing the bird's chasing the dog's chasing me. The dog that the bird that the cat chased. This is related to a famous example in linguistics, which was a recursive analysis of the chant bulldogs, 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 fight, 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 interpreting it as bulldogs that bulldogs fight, fight, fight. Naturally. Also like that. Okay. So can we do this? Well, sure. Why not? We can say with compound noun phrases, which are a phrase with multiple parts, and we'll give a recursive depth n. One recursive depth 1 version of this, as a base case, is just to take a phrase from the nouns table. So one kind of noun phrase is just the dog. Well, what if I want the dog, the bird chased, or the dog that chased the bird? Let's do that one. Then we can just say select the subject's phrase and then concatenate that with that chased and concatenate that with the object's phrase. Where what are these subject and object? Well, let's get compounds as the subject and nouns as the object. And if we want, we can say where it's the case that the phrases are not the same, so we don't get boring sentences. And we also want to make sure that this doesn't run forever. And so we can have a maximum amount of recursive construction. Here we'll just say n equals 2. And that means we need to define what n is for every case. So here in the base case we said n was 1. Here we'll say n is whatever n was before, plus 1. Okay, this is all a local table. Once you've created the local table, you have to create the select statement that uses that local table for something interesting. So we can use a different verb here, like pursued. And let's use compounds as the subject. And let's just use nouns as the object so we don't get ourselves confused. I don't think we need this anymore. Okay, what have we done? An error. Unacceptable. Thank you. Oh, here we go. So then we get the bird that chased the cat pursued the bird. That's not that exciting. What if we change this to 4? Now we get some really interesting relationships. We get the dog that chased the cat that chased the dog that chased the bird pursued the bird. And there are many of these. Because of course there's things like the dog that chased the bird that chased the cat that chased the dog pursued the bird, etc. And this is a shorter version. So the cat that chased the dog that chased the dog that chased the dog pursued the cat. Well, actually that's not shorter. But somewhere way up here there's a shorter version. Like that one. The dog that chased the cat pursued the cat. So why did I do all this? Well, just to show you that the recursive structure of language can be modeled by computers, at least to some degree, but having some ability to build up things recursively is the only way that we could possibly cover the space of all possible sentences in a language. Yes. some clause within select tells you what table gives you all the starting rows. So you can use table names there. The as part just gives you aliases. And if you have multiple tables separated by a comma, that means you join those tables together, or take all pairs of rows from each. So I'm taking every possible compound and every possible noun, and using those as the subject and object in a sentence. Okay, let's do some examples with numbers. A table containing the inputs to a function can be used to go from the outputs of a function back to the inputs. So we can actually compute backwards if we have a table of all integers. So here's an example. Here's a table called pairs, where pairs has all pairs of integers up to 50. So it says, give me the integer table I with column n, which contains 1, and then one more than everything that's already in there, up to 50. So that will give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 50 as the I table. Now this says select a.n as x, b.n as y. Okay, let's not worry about that. It says, what am I selecting from? Oh, I'm selecting from the integers, joined with the integers. So that gives me every pair of a number and another number, like 25 and 32. And then that's exactly what I select. A.n is the 25, b.n is the 32, and x and y are the new column names I'm going to use. And here's a constraint, then make sure that A.n is less than or equal to b.n. So we have 25 and 32, but we don't have 32 and 25. We will have 25 and 25. Okay, so we can already write a function that adds stuff together or multiplies. But how would we run it backwards? Well, here I could just write the expression x times y equals 24, and this will tell me all pairs of numbers that multiply together to get 24. Okay, so that's exactly what I just showed you. I'm going to load it up, and then I'm going to select everything from pairs where the columns are called x and y. X times y equals 24. And that says, oh, I can multiply together 1 and 24, or 2 and 12, or 3 and 8, or 4 and 6. Or if I wanted all pairs of numbers that add to get 24, it'll tell me, oh, here's what they are, 4 and 20, or 5 and 19, or 6 and 18, etc. So this is cool. I write the expression x plus y equals 24, and it gives me all possible values that I could fill in for x and y. As long as I have a table of candidates, I can get the ones that satisfy some expression. Oh, so why don't we have like 20 and 4 in addition to 4 and 20, I think is the question. That's because when I built the table of pairs, I specified that the A.n is less than B.n. But if I didn't have that, there would be repeat. This might be the perfect example to end with. Oh, not this one. You want to do this one? Okay, we'll do this one. How do you list all Pythagorean triples? What are those? Well, those are the numbers that could be the lengths of the sides of a right triangle. So 3, 4, and 5 can be the sides of a right triangle because 3 squared plus 4 squared equals 5 squared. So here's the list of all possible Pythagorean triples. And here's a definition of how to compute them. It says, get the integers up to 20. just like I did before. So 1 is a base case, and then n plus 1 for every 1 that's in there, for every I, for everything that's in there. And then we say, give me A, B, and C from, okay, I have to join together some stuff, and then check whether or not it's the case that A squared plus B squared equals C squared. So what do I join together? Okay, so one suggestion is I take all the integers, and all the integers, and all the integers, and then I filter for the ones that actually have this Pythagorean triples property. That's a good suggestion. I take I as A, I as B, I as C, and then I want to check and make sure that A squared plus B squared plus C squared equals C squared. And the last constraint I put in here is just to make sure that we don't have 4, 3, and 5 in addition to 3, 4, and 5 by putting an ordering constraint. Okay, now we get to the example I really wanted to get to, which is the Fibonacci sequence. Oh, I'm so happy. Okay, so how do you compute the Fibonacci sequence? Well, you have to keep track of the previous number and the current number, so you can add them together to get the next number. Let me show you the structure. What we want is 0, 1, 1, 2, 3, 5, 8, 13. And the way we'd get it is by building up a table with the previous and the current number, and then selecting out only the previous one at the end. So this says build up the previous and the current, where the base case is 0 and 1, and then I always want to keep track of the last one and build up the next one. By adding together previous and current, that's the Fibonacci recurrence. That builds me a 2-column table. If I want only the first column, then I select previous from that. Okay, so less than or equal to what? Well, if we want to go up to 13, then we need some number that's 13 or bigger. Okay. There are many choices here. I picked 14 kind of arbitrarily. Have a good day, and I will see you on Wednesday. Do the survey!